Awesome. Well, thanks everybody for coming to this last seminar of the semester. We are really, I mean, personally, I am very excited to hear this talk. We have former alum, Mark Siemens here, and Mark graduated with a BS in engineering physics from Mines in 2003, and then moved up Highway 93 to Gila. That's at the University of Colorado Boulder, where he did his PhD work in the group of Henry Kapteyn and Margaret Renan. After graduating from that group, Mark moved down the hall, still in Gila, to join Steve Kunda's group as an NRC postdoc. In the fall of 2010, he moved down Highway 36 to the University of Denver, where he is now a professor. In his research, he studies the physics of optical vortices and coherent electron dynamics in semiconductors. He's also the SPS advisor and loves doing hands-on physics demonstrations for K through 12 students. Mark is a Keck Foundation Science and Engineering Research Grantee, an NSF Career Awardee, and a University of Denver top principal investigator. So that's awesome. We are super excited that you're here. We also have here one of our own, Mark Lusk, and I'm about to read some things that I actually didn't know, and I doubt a lot of people here did. Mark received his BS in electrical engineering from the U.S. Naval Academy in 1982 and a Navy nuclear engineering certificate in 1984, and subsequently served as a Navy nuclear engineer officer aboard the USS Theodore Roosevelt, CVN 71. After fulfilling his service obligation, Mark obtained a master's in electrical engineering from Colorado State University and a PhD in applied mechanics from California Institute of Technology in 1992. He then joined the Electrical and Computing Engineering Department of Iowa State University as an assistant professor with an experimental research program focused on millimeter wave electronics. Mark subsequently joined the Colorado School of Mines as an assistant professor of engineering in 1994 with his research program focused on computational condensed matter theory, so pretty broad swing there. He received also an NSF Career Award in 1995, was promoted to Associate Professor of Engineering in 1998, received an R&D 100 award in the year 2000, and started the CSM High Performance Computing Center in 2007, now in its 13th year. So Dr. Lusk became a professor of engineering in 2004, but eventually shifted to a professor of physics, thank goodness, in 2006, where he has been for 14 years now. His research investigates light matter interactions using quantum electrodynamics with a current focus on topological quantum optics. So a lot of stuff that I didn't know, but that being said, thank you so much. We really appreciate your willingness to give this colloquium. And with that, I'll hand it over to you.
All right, thanks. And hi, everybody. It's really fun for me to be back at Mines in this way. Mines has a very special place in my heart, as I think it does for all alums. And so it's really fun to be here. I'm in sort of a unique situation. So I'm actually not in Denver. I'm up in the mountains in Salida, where my wife's family is from. We're not quite in a log cabin, but the internet is a little bit slower than Mark Lusk's and my comfort level. And so I'm actually going to turn off my video in a second and mute myself here and talk to you through my phone. So we're going to do that here. Unmuted there.
Muted here. Okay.
Turn off your mute microphone too. Yeah.
There we go. Okay. All right. So this is going to be a different colloquium than I've ever seen, and probably you've ever seen, in that there's two of us tag teaming it. And so I'm the experimental side, and so you get to see both sides, because Mark Lusk is the theory guru, and so he'll talk to you about some cool quantum mechanics applied to optics, and I'll tell you about how you actually do this stuff in the lab. So there's kind of three stages to our talk. The first stage is I'm just going to introduce optical vortices. A lot of work has been done in the last 25, 30 years on them, and normally in the context of orbital angular momentum and Laguerre-Gaussian modes. That's that figure in the lower left. And then I'll move to what we're currently working on now, which is thinking about putting more than one vortex into a laser beam and seeing how those vortices move. Like, do they influence each other as they propagate? So that GIF there is showing you two opposite charge vortices, and then you see Z increasing, the propagation distance is increasing, and eventually they recombine, and there's no vortices in the beam anymore. So we're trying to understand the physics of that process. And out of that, we realized we need to have a much better basic understanding of the theory of this. And so that's where Mark Lusk is going to come in and tell you about the theory that he developed. I helped him understand some of the basic optics, but he really took the lead for sure on the theory part and developed some brand new ideas for understanding these vortices that make it possible to understand this with fluids. Okay, also, I'm going to be saying next a lot because he's controlling the slides. So next, we should be on slide 2 now. Okay, so let me tell you about optical vortices and laser beams. And before I tell you about optical vortices and laser beams, let me tell you about just laser beams. So a typical laser mode has flat phase fronts. And what differentiates a laser from, say, the sun or any other star or a light bulb, right, is that we have this coherence. And usually we think of that as being a flat phase front across the beam. So you can represent that in the top image here with the 3 planes. Each of these planes is a flat phase front. So all the way across there, across one of those planes, is that the phase is constant. And then if you go back to the next plane, that would be one wavelength away, and you'd have another plane of constant and same phase. You can also represent it, and I'm going to do this a lot in our talk here, is to show this in one amplitude and phase combined diagram. And so here you're seeing the brightness is showing you the amplitude, and the color is showing you not the color of the laser beam, but it's showing you the phase. So all the way over on the right there, you can see that phase scale from 0 to 2 pi. So the fact that this is red just tells you that this has 0 phase, and the phase is flat, it's constant across the beam. So next we should see, what does phase mean for laser light? Just to make this very concrete for you, let's say we have linear polarization, then we know that the electric field component of the electromagnetic wave is oscillating up and down. And so the phase tells you at some instant in time the orientation and magnitude of the field in the course of that oscillation. All right, next we should see slide 3. So I'm just showing you a picture of a wave here. So the idea is that, all along the crest of that wave, this is coherence. All along there, that wave is in phase. If you go back, you can start to see the next wave crest forming. That would be one wavelength, and you've got another place of coherence. So all the way across there, there's coherence, and we have a similar thing with our waves here. Next on slide 4. So now we see what happens when you introduce a vortex. So let's start with the image on the right that says L equals -1. You'll notice that the phase front now is no longer a flat disk. It's actually a helix. So the phase is described by e to the I L, in this case -1, times phi being the azimuthal angle in the polar coordinates. And now our representation on the bottom with the brightness being the amplitude and the color being the phase, you see it goes red, yellow, green, blue, and then back to red in a clockwise direction. So if you click next, then you'll see that arrow going in a clockwise direction. So by the right-hand rule, we'll call that a negative topological charge. It wraps once, so we'll call that a charge of -1. The figure right next to that with the L equals +2, this is now a double helix for the phase structure. And you look at the phase diagram in the bottom, next you'll see those 2 red arrows. So this wraps 2 pi twice, and it does so in the counterclockwise direction. So we call this a topological charge of +2. Next, you'll see just, the water analogy. This is like a vortex or the swirling going down your tub drain. Next on slide, I think it's 6. I can't see the background because it's white. Angular momentum of light. So I just want to make this concrete for you to try to help understand the connection between, what kind of angular momentum this is, because this vortex carries real angular momentum. So the analogy is to classical mechanics. In classical mechanics, we have both spin and orbital angular momentum. And spin angular momentum is like a ball spinning or the Earth spinning on its axis, right? And in light, this has to do with the circular polarization. So every photon has either a +1 or a -1 h-bar of angular momentum that corresponds to left and right circular polarizations, respectively. And next we see for the orbital component in classical mechanics, we think about the Earth, rotating around the sun, orbiting the sun, and we see that's what the orbital angular momentum or this vortex component is related to. And here the orbital angular momentum, the angular momentum contribution of the vortex is L times h bar. So L could be any integer number, could be 1, 2, -3, anything. And so already you see this is a kind of an exciting playground for dealing with angular momentum, and a lot of people have explored this for applications in communications or particle rotation. But so that's one exciting aspect of these. So next on free space modes with OAM, a little decision tree here. If you're a theorist, you're going to talk about Bessel modes because Bessel modes are great. They're non-diffracting. They don't change with propagation. They have some challenges in that they require infinite energy and infinite spatial extent. So in the lab, we prefer to use Laguerre-Gaussian modes, which are just higher order Gaussian modes. You've probably heard of Gaussian, either Gaussian statistics, a Gaussian shape, a standard curve, a normal curve, normal distribution. And so that's the shape of a normal laser beam. That's normally what Dan and Jeff and Chip are trying to get in their lab. But in this case, we're looking at a higher order version that has a vortex in it. So these Laguerre-Gaussian modes, they have two quantum numbers that describe them. One is the azimuthal mode L, that's script L, which is exactly the same as what we were just talking about. That's going to be the vortex winding number. And they have a radial mode P, which I'll show you intuitively what that does in just a minute. So down at the bottom here, we've got the whole gnarly expression for one of these Laguerre-Gaussian modes. So it's not too bad. I'll just walk you through bit by bit. So the first part there, that grayish part, is just the normalization. So that's to make sure that as we change L or P, as we go to higher order modes, we still have the same power in the mode. The next term should be familiar. That's just the normal Gaussian. The next term is what gives us the donut hole. And if you'll notice that the mode in the top right there, we have a dark spot in the middle. So the reason is that we have to have a dark spot because there's a phase singularity right in the center. So in the center of the beam, the phase is undefined because we're wrapping some integer of 2 pi as we go around the beam. So you can imagine wrapping closer and closer and closer to the middle until you are just at the exact center point. The phase is completely undefined. So the only way for this to be a physically realizable mode is for the amplitude to be exactly 0. And you could imagine lots of shapes that could give you something 0 in the middle. And it turns out that this r to the power of absolute value of L is what gives you the eigenmode of free space for these Laguerre-Gaussian modes. The next term there circled in blue is a Laguerre polynomial. That's usually neglected because for radial modes, p equals 0, which is what people mostly use. It's just equal to 1. But there could be some interesting physics in that term that we think about from time to time. And then the last term there is the spiral phase, e to the I L phi. So that's what we started talking about, this whole vortex idea. And that's where that angular momentum component comes in. Next slide, we see so there should be a diagram here showing you different L values and P values. And what we see, so this is just showing you some examples. And again, the color is not what we see in the lab, right? The color is just showing you the phase. And as you go from red, yellow, green, blue, and then back to red, that's a 2 pi phase wrap. So P equals 0, L equals 0 at the middle on the top there, that's a normal Gaussian mode. And then as you move down this table, you're going to higher radial mode index. And you'll see that each time you do that, you add an additional ring around the outside that's pi out of phase with the ring next to it. And then as you go to higher orbital angular momentum or higher L values, you add an additional 2 pi phase wrap as you go around the beam. You'll also notice that as you go from L equals 0 to 1 to 2, and as you increase P as well, the modes get larger. And this is, I mentioned earlier, people were really excited about this additional kind of phase space of having additional angular momentum that you could put into the beam. In terms of communications, one reason why this isn't really so exciting is that to go to those higher order modes, you need to have a larger and larger fiber, basically. And basically what you're doing is spatial multiplexing. So you could also just run other fibers or use other mode sets. So those larger beams require a larger mode. Just a quick note for those of you who are working with lasers, you may be familiar with Hermite Gaussian modes, which are represented in Cartesian coordinates, just XY instead of in polar coordinates. And you can convert back and forth between these. So an L equals 1, P equals 0 Laguerre-Gaussian mode can be written in terms of a 1, 0 and a 0, 1 mode with the correct phase between them, with a pi over 2 phase shift. Okay, next slide, generating optical vortices with holography, slide 9. So here's how we actually do it in the lab. There's a number of ways of making optical vortices. We use holography. And so what we do is add whatever phase we want to put onto the beam. Let's just say it's a spiral phase, so like that little rainbow pinwheel there. And then we're going to add to that an e to the I kx, which is just give you basically a grading term. We add those two, we take the absolute value, and what we're left with is there on the right, the top right. You see it looks like kind of a normal diffraction grading, but in the middle, it's got this fork, this topological feature. And so what we've done is encoded the phase that we want to put onto our beam into this grading. And through holography, whatever diffracts off of this hologram is going to acquire the phase that we programmed onto it. And so down on the bottom, you see a simple picture of how we actually do this in the lab. I say a simple picture. This is exactly what we do. It's not that complicated. So we take a laser, we put in a spatial filter just to clean up the mode so that we have a nice Gaussian mode coming in. And then we use a spatial light modulator. So this is just a way to have computer-controlled, real-time updatable holograms so that we don't have to develop a hologram, and then if we want to switch, pull it out and put in another one. So we can do everything computer-controlled. It's just imagine taking like the screen from your computer and hacking off the back and sending a laser beam through it. And now each pixel, instead of controlling the emission of light, is going to control how much light makes it through. So we can put these holograms directly on there and control them with the computer. And then we block the reflected beam. That's what's coming off at the bottom there. And then the diffracted beam picks up exactly the phase that we put onto it. All right, next slide, slide 10. So we were talking about phase, and the vortex is all about the phase structure, or the phase structure is all about the vortex. You really need to have that phase there. And so if you want to measure a vortex, you really need to know the phase. And it's hard to do that. It's hard to measure the phase because every detector we have is really based on just measuring the intensity, right? Our eyeballs, solar cells, or photodiodes, those are, or CCD cameras, those are all based on measuring the intensity of the light. So the way to get at the phase information is to use interference. And so the first thing to do is to just interfere the mode that you have, that you get, say, from an OAM generator with, let's say, a plane wave or another Gaussian mode, and you look at the interference between those two. So that works really well, but the problem is you can't recover the full phase because there's a inverse cosine problem if you work through the math. And so what we do is use phase shifting holography. So we use 4 different reference beams. Oh, next, you should see test phase plus a whole bunch of stuff. We use 4 different reference beams, and you could do this next by scanning a delay on your reference beam. But what we do instead is get rid of the separate reference beam, and we put the reference beam onto our hologram. So we have a composite hologram that has 2 parts. One is the phase of the thing that we're trying to actually measure. And then we make a second contribution to it that's just a Gaussian reference beam. And then we can shift the phase as you go. Look at that middle column with the kind of the jail bars. As you go from the top to the next one, you can see that those bars are moving over a little bit. And what that's doing is shifting the phase of the Gaussian, the reference component. And if you look at the far right, you can see those pinwheels spinning slightly. And the direction of that spin is going to be determined by the sign of the topological charge. So next you see this equation here with kind of a picture is inverse tangent of the 3 pi over 2 interferogram minus the pi over 2 interferogram divided by the 0 interferogram minus the pi interferogram. We do this calculation and we recover the phase. So this is not a algorithm. It's not a search. It's not a some sort of attempt to check or guess and check. We are directly calculating the phase in this way on a pixel by pixel basis. So next you should see phase measurements, modal decomposition. Yeah, slide 12. So here's some examples of actual measurements we did. So I want to emphasize the rainbow colors here are actual phase measurements. Everything I've shown you to this point has been Mathematica. I plug in an equation and look how beautiful it is, but these are actual measurements from real laser modes. So the left 2 columns are hypergeometric Gaussian modes. They have some additional rings on them. And then the next 2 columns are Laguerre Gaussian modes. So those are the ones we were talking about earlier. So you see one with L equals -1 and L equals +4. You can see they spin the right direction and they've got the right number of 2 pi phase wraps. The one on the right is kind of fun. It's hard to tell on the top, but it's actually also a donut mode. So it's dark in the middle. So if you were to just look at this in a lab, you'd say, oh yeah, I got a vortex there, I got a dark spot. But if you phase resolve it, you see that the phase is actually flat because we played games to get a mode that's it's a composite mode that has a flat phase but is dark in the middle. So that emphasizes the importance of actually doing the phase measurement. And then once we have the amplitude and phase like this, we can do like you would do in any quantum mechanics problem and put that into the whatever basis you want. And so we can put this into a Laguerre Gaussian basis, for example, but now we're taking actual measured data and doing that. And so, for example, on the lower right there, you see for Laguerre Gaussian mode, this is the spectral power for the different orbital angular momentum or vortex charge numbers. You see that's on a log scale. So we have a 99.9% purity into the L equals -1 case. In L equals -1 vortex charge in this case, which next to our knowledge is the highest purity vortex that was ever measured. So on slide 13 now, so I want to transition now from talking about orbital angular momentum, like our Gaussian modes, to thinking about what happens when you put more than one vortex. And we're going to talk a lot about two vortices because that's the next simplest thing to talk about next. So basically the question is, what happens when two or more vortices are placed into the laser beam? All right, slide 14. So we're going to think about vortex interactions. We want to measure vortex pair motion. So the first thing we need to do is to generate a vortex pair. And so we're going to use the same method we did before, but now instead of just putting a single vortex in there, we can create some array of vortices. So this example here, I'm actually showing you a 2x2 array just to kind of illustrate the level of control that we have. So we can control the amplitude and phase at every point on the beam, which means that we can control the vortex charge, plus or minus. We can control its location. We can control its tilt, which is something that you'll hear about more in a few minutes, and some relative phase information. So we really have exquisite control of the initial configuration of these vortices using this spatial light modulator approach. And then if you look on the top right there, you see a CCD with some arrows. What we can do is put a CCD camera on a stage and just drive it back and forth to measure what the mode looks like as it propagates. Okay, next. So here's our pilot study, a measurement of two vortex motion. So this is just a little bit more detailed schematic of the setup. So we use an imaging system. So the SLM is there in the middle. And then after that, there's there's two lenses around an iris. So the iris selects just the diffracted mode that we want. And then the two lenses basically image so that we can run our camera and start right at the SLM plane and then back off from there. Because we're going to generate, so our laser beam is coming in with some, it's a Gaussian laser beam, and then we're going to put two vortices in there and see what happens. Okay, so then on the lower left, you see two GIFs running. The one on the left side is two vortices with opposite topological charge. And you see that as Z increases, as that propagation distance increases, so we're scanning the CCD camera back, you'll see that the vortices move down and start to drift towards each other and then eventually recombine, and there's no more vortices. The example next to it is for two vortices that have the same topological charge. Those kind of move slightly apart maybe, and maybe a little bit vertically away from each other. But there's certainly not the same recombination motion and much slower vortex dynamics in general. So next slide. So here's our results for two vortices. And so the top frames there are showing you the results for the plus minus charges. You can see as the propagation increases, the vortices move towards each other and recombine. For two positive charges, they maybe rotate a tiny bit, but are pretty much stationary. On the bottom, I'm showing you the separation distance between those vortices as a function of propagation distance. So as Z increases, you're moving off to the right. And the red dots are data for plus charges, and you see they basically, they don't separate at all. And the blue dots are the opposite charge pair. And those start pretty much constant separation, and then they dive and eventually recombine and go to zero separation. On the right, you can see the data kind of like a head-on view with just scatter plots as they are accumulated. So the top is the plus minus charge pair, and they start along the zero line far away from each other, and they move upwards, one on the left and one on the right, until they recombine at the top middle. And then in the bottom, you see the red dots, that's the plus charge, and you see they pretty much stay in the same place. So you'll notice the plus minus charges, they seem to follow kind of a half circular sort of trajectory, and the plus charges seem to be pretty much stationary. All right, next slide. So we wanted to understand the physics of what's driving this vortex motion. We could decompose this in terms of Gaussian modes and just write out a mode basis and propagate the thing. But we really wanted to understand this from a perspective of what's driving the vortex motion itself, because this is a very rich field in, for example, quantum fluids, looking at vortices in superfluid helium or Bose-Einstein condensates. There's a lot of really interesting work going into understanding how those vortices move, and we wanted to see, could we understand that for these vortices? So let's talk about superfluid vortices on the left here. So I've got two examples. One is a plus-minus pair, like we talked about, and one is a plus-plus pair, kind of like we talked about for the optics. So in superfluid, you think about one vortex is driving, so if you have a vortex pair, each vortex is going to move in the background field of the other, or the phase of that spiral phase of one vortex is going to influence the other. So next, if we look at just at vortex 2 over there, the one on the right, and we think about the background field from vortex 1, and we take the phase gradient of that. Think about it as being kind of a wave that vortex 2 is going to be riding. We see that phase gradient is pointing down. Next, we look at the spot of vortex 1 and think about the phase gradient from vortex 2. That's also pointed down. And next, now you should see white arrows on the top left diagram. That's showing you what these vortices are going to do. If you have a plus-minus pair in a superfluid, they're going to track together. They're going to move down in this case. Or if it was plus-minus instead of minus-plus, they would move up. Okay, so now let's turn our attention to the plus-plus case. Next, you should see specializing to the vortex on the right. It's the background field it experiences is the field from the vortex on the left. And so that background, the phase gradient there is pointing up. If we look at the background field on the vortex on the left, it's experiencing a phase gradient pointing down. So those are in opposite directions. Next, we should see these two white arrows in the top diagram. And so what happens with 2+ vortices is they'll actually spin around each other in a counterclockwise direction. If you have two negatively charged vortices, they would spin in a clockwise direction. So I said this is vortex motion in a superfluid. It's also true in cyclones and hurricanes. So here's a snapshot from a weather forecaster explaining the Fujiwara effect in hurricanes this summer. You had two hurricanes that were coming close to each other, and they actually can experience this sort of orbiting. So that's known as the Fujiwara effect. Okay, so what's happening in our laser beam? Next, we see our minus plus and plus plus situation, vortex motion in a laser beam. Next, our white arrows, we see it, we saw kind of a half circular sort of trajectory for our minus plus, and the plus plus were basically stationary. So if you compare these two situations, clearly things are very different. So next, that makes us think maybe the hydrodynamics explanation fails to explain optical vortex dynamics. Or next, maybe there's more physics. So there's a really important difference between the vortex dynamics that we see, just between the vortices that we see in a laser beam and the vortices in a superfluid or in cyclones. And that difference comes down to the amplitude structure. So in the lower right here, I'm showing you the amplitude. You think of these as a fluid, as a function of distance away from the vortex center. So the blue line there, you see that basically absolute value of distance away from the center. That's what it looks like for an optical vortex of +1 or -1 charge. So if you remember back to the Laguerre-Gaussian expression, a +1 charge vortex has a core, an amplitude core of r to the 1. And so that's why it's a linear shape like that. In contrast, the superfluid vortices are basically, they have basically a constant density, except for a little blip right in the middle. To the size of that little blip they call the healing length, and it's usually in the order of angstroms, so it's really tiny. And so they don't have the same sort of amplitude modulation that we were seeing in our optical vortex case. So we thought it looks like there really is some more physics going on here. And so that's where we asked Mark Lusk to help us figure out the theory here.
Thanks, Mark. So the starting point for us is Maxwell's equations. Everything that Mark has been talking about is associated with Maxwell's equations, and here they're embodied in a wave equation for the magnetic vector potential A. So this is the equation that we start with in trying to understand what's going on with these optical vortices. And we assume a particular type of solution for A, and it looks like we're just talking about a plane wave where the light is polarized in one direction. But in fact, this psi here is a field. Psi depends on x, y, and z, where z is the propagation direction of the beam. And so psi is not just a constant. In fact, if we take this A and put it into the wave equation, we have a new equation, a scalar equation for psi. And here I've broken down what would be the Laplacian into two pieces. So this little perpendicular symbol, transverse, means that this is the Laplacian in the xy plane, perpendicular to the direction of propagation. And here's a second derivative of psi broken out along the direction of propagation. And the reason that I do that is because it's a second term that's normally quite small for beams of light. That's called the Paraxial Approximation, wherein we just drop this. And if you look at this equation and kind of blur your eyes, you see that, here it is again, that it looks like the Schrodinger equation, which I've drawn over here at right. And the only difference is that the Schrodinger equation is in terms of time, and what's called the Paraxial equation is in terms of z. And so from here on out, I'm going to refer to this Maxwell equation, this Paraxial equation, as a Schrodinger equation. And I'm going to think of z, the direction along the axis, as actually time. And so what this does is it turns everything we're doing into a consideration of two-dimensional physics with this new type of time-like axis. And it's because it's two-dimensional that all sorts of interesting topological features can be exploited. Now let's talk about, before we even talk about lasers, let's just talk about light and touch base with what Mark Siemens was saying about it having a hydrodynamic aspect. So light, it turns out, is a 2D compressible fluid. Let me explain why I say that. If you take this Schrodinger field psi and decompose it into an amplitude rho and its phase phi, then you could think of a fluid density as being the square of the amplitude, and we'll call that chi, and the fluid velocity, something that Mark already mentioned, as being the gradient of the phase. How do I know that? Because if I take this expression and put it into the Schrodinger equation, the Schrodinger equation magically turns into Euler's equation for a two-dimensional fluid. And that's called the Modal transformation. And the right-hand side here is the gradient, the transverse gradient of the pressure, where the pressure is given in terms of the density. And anytime you have pressure related to density, it's like a spring with strain related to force. And that means that the material is compressible. And so the Schrodinger equation, or Maxwell's equation, has turned into an Euler equation for a two-dimensional compressible fluid. And so we think of light as being a two-dimensional compressible fluid. Okay, now let's talk about vortices. And I'm going to take a step back. And instead of talking about compressible fluids, let's make a foundation based on something that Mark Siemens had just talked about, which is an incompressible two-dimensional fluid. And in an incompressible fluid, we think of the fluid as being a background, and we just kind of plop in a vortex, a little point vortex into that fluid. So when I talk about the background field, I'm talking about an incompressible fluid, say, that has a vortex on top of it. And one of the things that we know, it's been known for a couple hundred years about incompressible fluids, is that the vortex moves with the fluid. It's called advection. And so if I know the vortex, or if I know the fluid velocity, I also know the vortex velocity. And we know from fluid dynamics that the fluid velocity is given by the gradient of the background phase. So that must also be the vortex velocity. Okay, so for an incompressible fluid, this is an equation of motion for the vortex. And what we want to do is come up with an equation like this that tells us how those vortices move and eventually annihilate, the experiment that Mark Siemens showed. So let's extend this a little bit into compressible fluids. We still have this decomposition of a background fluid field and a vortex field. That's our total Schrodinger field. We have this Schrodinger equation, the Paraxial equation. And now we take this equation and play a little variational game. All we do is say we want to track the place where both the real and imaginary parts of psi are equal to 0. And so a little variational analysis actually gives you an equation for the velocity of the vortex directly from the Schrodinger equation. And here I've written it down. And what you see is that for a compressible fluid, sure, you have this initial piece, which is the fluid velocity, but now you have a piece that contributes to the vortex so that the vortex doesn't any longer move just with the fluid. Instead, the vortex can move relative to the fluid because of a gradient in the background density of the fluid. Now, we didn't invent that. That's been around for about 14 years. In fact, it's been refined several times, and most recently in, I think, 2018 by a fellow named Groshek that was nice enough to suggest to us that we look at this and maybe it would be useful. So we're very appreciative to him for helping us out in that way. All right, so let's see how this works for maybe, all we need is that equation by Groshek, and maybe we can track our vortices directly. Let's see. So we put in a Gaussian beam, and initially there's no phase. So this gradient in the phase is equal to 0. And if you actually put in the expression for the radial change in the density of this Gaussian beam, and you put a vortex on the shoulder of the Gaussian beam, then the vortex will move straight up. And that's what this equation predicts. So we're thinking, oh, great, this equation that Groshek suggested to us is beautiful. It does predict exactly what the vortex does. But then we tried it for our system and it didn't work. And the reason that we thought the difference might be is because our vortices started as circles with circular contours, but they developed into elliptical contours and got more and more elliptical as they went along. So we started thinking, maybe this elliptical thing is important. Maybe we have to include that in the dynamics. And we screwed around with this for a while and eventually decided that the way to go was to think of this picture that you're seeing right now as the projection of a three-dimensional object. And so we think of this as a true three-dimensional vortex that is sticking up out of the plane of the paper here, and the projection axis, that the flashlight, if you will, shining down to make the shadow that you see, is actually a gauge freedom. We can choose any projection axis that we want. In fact, that tilt of that three-dimensional axis can be described by two angles. And so we have a way of describing these elliptical vortices using two Euler angles. And then it raises a couple of questions for us. Can we predict the vortex tilt from the Schrodinger field? And maybe can we figure out how this tilt affects the dynamics of the velocity of the vortices that we see in the lab? So here's the picture. The red circles, the red ellipses are the shadow, what we would actually measure in the lab. The green is all in our mind with a gauge freedom in terms of what the projection axis is. And we choose this projection axis as Z prime, and we call the two angles here that describe that axis as the azimuthal angle, C, and a polar lean, the leaning of Z into Z prime, as theta. And so now our game plan is to be able to figure out how to measure C and theta from the paraxial field, the Schrodinger field, and how to use that to figure out where the vortex goes. Okay, I'm thinking of my friend Ruben Collins, who says, man, theorists love to show a bunch of equations. All right, so sorry, Ruben, I'm going to show a bunch of equations, but only briefly. Okay, so it's all we have. The first step here is to describe the tilt, these two angles in terms of the Schrodinger field. And the way we do it, I think, is kind of fun. You take the Schrodinger field that has real and imaginary parts, and you turn it into a two-dimensional vector. And then you play a game in continuum mechanics. I mean, my PhD was in applied mechanics. I got to use it for something. So I take the gradient of this two-dimensional vector, and that makes a tensor. And I think of F here, not its inverse, as being the deformation gradient, like the gradient that the deformation gradient associated with the twist of an elastic continuum, or associated with Navier-Stokes, the deformation of a fluid. And if you think of F as that deformation gradient, you say, oh, any tensor can be decomposed into a symmetric part and a rotational part. And the symmetric part includes all the stretches and the special axes associated with the ellipse. In other words, if I solve the eigensystem of this symmetric tensor V, here's the eigensystem in terms of the eigenvectors and eigenvalues, it's not too hard to show how those values relate to the two angles. Okay, lots of math, but what is it saying to you? It's saying you solve the Schrodinger equation, and I'll tell you, given that field, exactly what the tilt of the vortex must be. And that's powerful. All right, the next thing we decided to do was to take those tilts and see if we could somehow figure out how they might be affecting the dynamics. Well, remember, an incompressible fluid just looks like this. The vortex velocity is the gradient of the background phase. And the compressible stuff, the stuff that Groshek suggested to us, had this additional term, okay, associated with the gradient in the background density of the fluid, if you want to think in terms of fluid. What we did is a variational analysis, just like the one that they did to get this term, only now we allowed for tilt. And it was fun, and the result is something quite different. This is the same equation, but now there's an additional tensor, and this tensor is acting on that background gradient in the density. In other words, this term right here includes all of the tilt stuff. So we have a tilt operator that's screwing around with the background density, and now they're coupled together. All right. This is like a surfer, okay? And the surfer can now lean their body, and if they lean their body, they can change the direction that they go in. So now we see that the vortex can now affect its own velocity by tilting. And that's important, and that's what we're actually seeing in the lab. So these vortices are really 4 degrees of freedom systems. There's two degrees of freedom associated with position, and 2 associated with the tilt angles, like C and theta. Now we can turn this back to the lab and see if it makes sense. So we looked at 2 applications, and one of them was particularly simple. It's just this Gaussian, where I'm looking down on the Gaussian now, and I put in an elliptical vortex, something that Mark Siemens can produce in the lab. This is still just modeling, though. And the paraxial field shows you the contours, the solution to the Schrodinger equation at some later time here. And if we take the Schrodinger field and then go through this three-step process, we take the Schrodinger field to get and solve for the tilt. We use the tilt to get the coupling to the density, and we solve to get the velocity, and we integrate it, we get this green line. And so the green line is predicting the track of that vortex pretty well. And so we thought, oh, okay, this is working like we had hoped. All right, so now we go to the lab. And on the left is the theoretical prediction. On the right, for this particular set of angles, is the X and Y positions of the vortex as a function of time. The dashed lines are the predictions from our theory, our vortex equation that we've integrated. And the discrete points are what Mark's group measured, and in particular, a really great student named Drew Votief did this. And wow, you know, it's easy for me to show this, but it took him months to get this stuff right. And because it's a really difficult experiment. But the standard deviation is given with the error bars. As you can see that the prediction and the experiment match up within the one standard deviation, which is really excellent. So Drew did this again. Now we tilted the vortex so that there's an azimuthal component, and you can see that the trajectory is now at an angle. And once again, Drew's measurements are exactly on, that we can match up the experiment and theory within a standard deviation easily. So then Drew goes crazy. Not goes crazy. He does a great job, and everything's compacted into this one plot, but each point on this plot is a different experiment of Vx and Vy. And let me talk you through this by just looking at one point. If I look at this light green circle up here, the way to read that is to say, I'm on a line with theta equals 60 degrees. That's the polar lean. And I have a number up here in colored. That is my azimuthal orientation of the vortex. The green circle in the middle is my prediction for what the vortex velocity should be. And the black dot is what Drew measured in the lab. The circle around it is one standard deviation associated with his measurements. And there's two dimensions to that, you know, Vx and Vy. And all of these plots you see, the idea is that the colored dot should be near the black dot. And it is in every case except, wow, you'd think this would be the easiest, but it's not. The one where there's no tilt at all, and then we're a little bit off because the vortex drifts a little bit as it goes up. But the bottom line is that the measurements that we have made here now pretty extensively are consistent with our theory. And so we're of the mind that we've captured the right theory, at least in the simple setting, and now we can turn back to the more complicated setting of the annihilation problem that Mark Siemens talked about. Now, he talked about the top half of this, where two vortices are coming together. But as long as you're doing that, you may as well, this is easy for a theorist to say, you may as well start with the nucleation and look at the whole circle. So you can nucleate these two pairs, have them move up and separate, and then eventually come back together again. And we're going to follow the same approach as what we did with Drew's experimental work. We solve our Schrodinger equation to get psi. We use psi to get the tilts. We use the tilts to get the velocity. We integrate the velocity to get the position of the vortex. Done. All right. Still in theory land here, but just to get an idea, these are pictures similar to what Mark showed, where I'm looking at the magnitude and the phase of the Schrodinger field, this paraxial field. And because the field is so simple, it's possible to analytically determine the position of the vortex as a function of time. In fact, that was done almost 30 years ago by Indebito. And so we're going to use that to help check ourselves. The black line here, the black curve, is the Indebito prediction for where the trajectory should, what the trajectory should look like as these two vortices come together. And you can see that the vortex pair is moving as I go through these 4 time slices until it finally annihilates at this last slice. And so we take that, we say, okay, what's happening with the tilt? Oh my gosh, it's so complicated. This is the tilt, and now there's 2 angles, two sets of angles, one for each vortex. It looks pretty crazy. And so we're trying to make sense of this. We think, hey, let's just plot this on a 3D plot. And it looks like this. And now we can kind of make sense of what's going on. Down here at the lower right, you have a nucleation event. And one vortex goes off to the left, one vortex goes off to the right. You can think of time, the beam axis, as being vertical. And eventually there's a nucleation. And our experimental work is going to be with this top half. the nice thing about this is that you can see the vortex tilt as a function of time, and you can follow both vortices. And if you don't realize that time is pointed up, you say, hey man, you just have one vortex. It's just going around in a circle, right? With this continuum of tilts. And, you know, it's kind of like a Feynman diagram in that sense. Sure, it doesn't matter how you look at it. It all still makes sense, right? So this kind of makes sense and makes us think, okay, we think we know what's going on. Let's see if this ties in with what we actually do in the lab. All right, the way we're going to do this is in pieces. First talking about just the theory still. Here's that in debito trajectory. If our vortex velocity equation works, the velocity should be tangent to this at every point. Let's check that. This is an incompressible, the direction of the vortex for an incompressible flow. So if I rule out everything but the incompressible prediction, the vortex would move straight up. And we see, no, that's not right, but we already knew light was compressible. So then we include this Gaussian term that is associated with the gradient and the density. And honestly, this is the thing that we had hoped originally was going to work. So when I first plotted this and Mark Siemens and I were looking at it, we're like, what? It doesn't work. I can't believe it. But then we went through a few months of work and he pretends like it was me, but we were both working on this together every day. We finally had this term, and when we include it, the velocity is now tangent to the trajectory. And in fact, if we integrate the velocity, we do get exactly analytically that blue line for this simple case. So we're feeling pretty good about being able to do this. We go back to our experiment and now we plot the predictions. The blue curve, let's just focus on that one, is our prediction for how the vortex separation works as a function of time. And it's matching up with the experimental stuff pretty well. But now we can do something completely new. We can use our theoretical expressions for the vortex tilt, and we can actually use those in the lab to back out what the tilt of the vortices are experimentally. And so we're plotting the theoretical predictions on the horizontal, and the vertical, on the vertical, it's the experimental measurements. And we're comparing those, ideally to be along a 45-degree, and we're pretty darn close. One standard deviation is the shaded areas here. And honestly, these are really hard experiments, easy for the theory side, but hard to do experimentally. And so it was actually surprising to us that we got within a standard deviation for most of the data points. All right, let me pull this together and summarize a little bit. We're playing in this area of topological optics. That's what this really is, where we have optics in 2 dimensions and there's structural features, and that's the topology. So we have 2 + 1 dimensional physics of this topological compressible fluid. It's very much like a dilute Bose-Einstein condensate. In fact, with the Feshbach resonance tuning, you can change the amount of nonlinearity in a Bose-Einstein condensate and make it look very much like one of these optical fluids. The system that we're looking at has 4 degrees of freedom. Now we understand that, 2 tilt angles in addition to the transverse positions. We have what we think is a kind of a new dynamical theory associated with these vortices. And the important thing is not just that it explains what we saw in the lab, but that we can exploit it to actually move the vortices around, many vortices, and we can braid them. We can think about information transfer or encoding of information in these things and the motion of the vortices, and that's really where we're headed. We've also looked at Bose-Einstein condensates, and we've applied all of this, even though I didn't really talk about the derivation. Everything that I showed you applies equally well to a nonlinear Schrodinger equation. And so we're able to make predictions for nonlinear materials and include the trap of the Bose-Einstein condensate and predict how the vortices move in there. And with that, I'm going to turn it back to Mark for a couple of final comments. Mark?
All right, thanks, Mark. So where do we go from here? So we see this as a system where we can look at the optical vortex interaction and really do room temperature quantum science in what we're calling topological fluids of light, or topological optics, and leading to questions about are these vortices, can we treat them as emergent quasi-particles? We have direct control and readout, right? So compared to other systems for doing quantum science, where you have to do things at really low temperature, the coherence of the laser beam is easy. And so we can do this out in free space. And if you want to know what happened to the beam, you just stick in a camera and it's all at room temperature. So we see this, the diagram over on the left, the Venn diagram, as kind of a unique triple point between condensed matter and particle and optical physics. And we're looking for more people to join the team. So in particular, if you're interested in looking for a PhD, or if you have students looking for a PhD, I'd love to chat with you. And next, so thanks to especially the WM Keck Foundation. So this talk with Mark Lusk and me here brings back memories of our talk in front of their panel, and just a lot of fun we had when they came to do a site visit and eventually very generously supported this work. And then also thanks to a number of people in the group, in particular, Jasmine Anderson and Drew Voitiv took a lot of the experimental data that you saw here. So yeah, feel free to contact me by email if you have questions or interest in this topic, and we'd be happy to take questions now. Oh, I also wanted to mention, if you are interested in grad schools, DU is in the top 10% in terms of percentage of women in the graduate program, which is unique. Mm-hmm.
Awesome. Wow. That is incredible. What a crazy analysis. That was really, really cool. So we do have a few questions if you both would be interested in answering some of these. So our first one is from David Schmidt, who says, have you looked at mixing different vortex beams of opposite but unequal charges?
Yeah, so I'll jump in there. So we've thought about it a little bit so let me just start with adding a single vortex of not the same, of a non-integer charge. So not plus or minus 1, but 2 or 33 or something like that. What you'll see is that if you put that vortex right in the center of the beam, it will stay as long as you've got pretty good propagation conditions and you've centered it as best you can. But as soon as you move it off center, you break the symmetry, and that, let's say, topological charge of 33 will break up into 33 unit charge vortices. So then you have to think about the motion and the dynamics of those three questions. Of all of those vortices. So that may be a next step, is to start to think about how those things split up and how they move. But for now, we've been focusing on the unit charges because those are the ones that are stable with propagation.
Let me add one thing there, Mark, we intentionally break them up sometimes, and we can break them up to make vortices do things. In particular, we can make them circle around each other in a braid, or we can make them scatter. We can have multiple vortices that scatter off of each other and sometimes nucleate additional vortices. So turning it around, that breaking up can be a good thing.
Yep.
Cool. So from David Goldberger, experimentally, how do you control the vortex tilt?
So we take the analysis that Mark Lusk showed you in terms of, we got this polar tilt theta and this azimuthal tilt C, and then we can plug that in and get what the field should look like. And then we just stamp that onto our hologram. So it's just, I showed you lots of examples with theta equals 0 and C doesn't matter for an untilted vortex, but then we just change our hologram to include the tilt in there.
Awesome. And I don't know.
Mark, are you looking at the Q&A, the questions?
No, not me. I'm just looking at Dan.
Well, I'm laughing.
You should open it up and look.
Mark Hassman says beat Navy.
Hey,
that's for you. That's for you, Mark Lusk. So,
Jay, there's no response required there. That's ridiculous.
So I'm gonna say that one was answered live.
Okay.
So this is Ruben, and I want to ask a question, but I think it's ill posed. Usually, these things that are governed by differential equations, usually in the first step of solving the problem, you're able to figure out how many degrees of freedom the solution has in it. And it sounds like in this problem, you started out with something that looked like it had 2 degrees of freedom, and it turned out in the end to have 4. And that's like, more than I would have expected. So in retrospect, does it make sense that there are 4 degrees of freedom, given, the physics of the problem? Did the question make any sense?
Yeah.
I think so. I get it. I mean, it was surprising to us. We didn't walk in thinking, oh, it's a 4 degree of freedom system. But on the other hand, it's a continuum field, and it's our eye that's pulling out the vortex as an object of interest, right? So when you pull it out, your first thought is the vortex is identifiable by the fact that it's a singularity. The density, the amplitude 0 and the phase is singular. And if that's your definition of a vortex, there's 2 degrees of freedom. But that's not enough to anticipate how the vortex moves. Now we can completely determine the motion in the problems that we've done. So we think there are 4 degrees of freedom. But isn't it like quantum numbers? I mean, you have a complete set when you haven't done any experiments for a long time that show you new quantum numbers. So I would say that jury's out. I mean, there could be a curvature effect here. We don't know. It's a good question.
Yeah. So Nick Mattery says, how does the theoretical treatment change when considering an open system? What types of unwanted interactions with the environment are present in optical vortex experiments?
That sounds like Nick. Yeah. I'm thinking, is that an experimental? Is that maybe?
I can tell you an experimental factor.
Yeah.
So one thing that we didn't talk about really, but that goes into it is that background field that we use to calculate, the gradient of the density and the gradient of the phase. That's not just determined by the other vortex, it's also determined by the beam that the vortices are moving in. And so when we do these recombination experiments with 2 vortices, what I showed you was data where the 2 vortices start pretty close together. And so that the gradients of the beam itself, at least to start with, are rather small, at least relative to the phase gradients from the vortices and the amplitude gradients as well. So when you include the density gradients of the beam, that is an additional factor that has to be included. It's kind of some aspect of the environment.
I would also add that in an open system here, it's less susceptible to noise and to the standard effects of an open system because of the fact that light doesn't interact with itself.
So I have a quick question before Mark Lusk has to go. So can you point me toward where you get this? So you wrote psi as a product of 2 psis. One is the vortex field, scalar field, and one is the background scalar field. Where does that actually come from? Do you have you probably had a reference or something, but I have not actually seen that type of thing done before. Usually in optics, right, we say that it's a sum of 2 things, not a product, but this is very interesting.
Yeah, this is a starting point for, this is an initial condition that we could program into our diffraction gradient, Mark's diffraction gradient, or we could put in as an initial condition for the Schrodinger equation, right? So it's just, I can assert that is my initial condition, and then I can follow it, and I can then assert that the vortex field is the same if you get really close to the vortex. And so I can always decompose it into the total field divided by the vortex field, and what's left is the background. So it's not a matter of wow, this happens to work out. It's more, I assert that there's a product at all times, and that defines the background field.
Okay. Because usually I would just write the background field as 1 plus something.
Right, but here, if you wanted to remove the vortex, that sum isn't going to work. You have a singularity, and you want to remove it. You need a product. The left-hand side has a singularity, and the right-hand side has a singularity, and the singularity is embodied in that psi vortex.
Yeah, that is really fascinating to me.
Let me say that one more way. The e to the I L phi and then potentially tilted of the vortex is in the beam itself, right? So if you try to write that psi as a sum with a vortex term and a background term, you're not going to be able to do it because the e to the I L phi it's everywhere, and so you can't just subtract it off. It's everywhere on all the amplitudes. So you really have to write it as a product. That's the natural thing to do with this phase here.
Yeah.
And maybe it's worth pointing out while we're looking at this, that something that Mark said at the very beginning, the background field of one vortex includes the vortex field of the other vortex or of the other 10 vortices.
Very
So the way that these guys talk to each other is by influencing their background field. If you were talking about this from a particle physics perspective, you would say that the background field mediates the interaction between two particles.
Hmm.
So the background field is bosonic, like that. Yeah.
That is so cool. Okay, so we have one more question here. I know, Mark, you have to run, so if you can't stick around, we'll just have to lean on Mark Siemens here. But Jonathan Barilak says, do these optical vortex dynamics show up / explain what is seen in speckle patterns? Can these vortices sort of spontaneously form in pairs, making weird speckle patterns for a flat beam?
That's all Mark Siemens.
Yeah, that's a prescient question, because that's actually where we started. So there's before we went to the two vortex case, we actually looked at speckle, and Dan came to my lab once and saw if you image speckle and you get to the very near field of speckle and then change the propagation distance, you can actually see this really crazy, it looks like it's biological or alive. The vortices moving around, and they do exactly what you're saying. They merge together, they pop apart out of nowhere, and it's always the plus and minus one charge pairs, and they form loops and all sorts of interesting dynamics. We did we tracked the vortices and did some statistics on them and found that the velocity statistics pretty much matches what you'd expect from a quantum fluid. So vortices in helium or Bose-Einstein condensate. And so that made us think, can we really understand the physics of how these vortices are really interacting, which is a weird thing to say, right? Even now it feels weird to say because we're in a purely linear system, right? So there is no interaction. The photons are not interacting. But if we take this vortex-centric perspective and look from the vortex perspective, they're riding in this optical fluid, and the motion of each vortex, or they're advecting, the motion of each vortex is driven by the presence of all of the other vortices in the system, and we can describe their motion that way. So yes, absolutely, speckle is a great example of this.
Awesome. Well, I think that might be, doesn't look like we have any other questions. So, and I think we're a little bit over 5. So if people want, I think the students can be dismissed. And then those of you who'd like to stick around and talk to Mark Siemens, feel free to stick around. And if Mark, you have to head out, that's.
I do. Thank you, everybody. I'm sorry that I have to run. I had a prior commitment.
Yep.
Yeah, thank you so much.
Thanks, everybody. It's really great to share with you.
And Mark Siemens, you're going to stay here, right? I'm gonna sign off on this, and okay. And this is going to disappear when I sign off the screen.
Oh, right, yeah.
Okay.
I can try to pull up a copy.
Okay.
If we need to.
Yeah. All right, you guys. Thank you very much. See you later now.
Thanks.
Bye.